Hello folks, my name is Amrit Agrawal and this is my demonstration for Project 9, IE590 Electro-Robotic Systems. This is a conveyor belt system which runs via OpenCV and Python. The main idea is that the Python program acts like a controller for the whole system. It loads on fountain pen images one by one from the project folder, processes each image with OpenCV to detect the pen's orientation, then sends a correction command to the servo through telemetrics and Arduino, and uses the RGB LED system to show system status. Red means that a new pen has arrived and is being analyzed, and green means that a correction has been applied and the pen has been aligned horizontally. I will go through the entire hardware of the system. I will show you how each piece of hardware is being connected. Then I will go through a live demonstration of the code, followed by which I will jump into some more nitty-gritties of how the code is being implemented and how we've implemented the system. Going over our Arduino board, the Arduino board is connected to my PC via its standard Arduino connector. We have two pins. We have two jumpers going from our ground and 5-volt pins on the Arduino board going over through the ground and 5-volt rails on our breadboard. We have an RGB LED module which has the resistor soldered on it. So I just am directly connecting it to the PWM pins. The red, green and blue are connected to PWM pins 9, 10, 11, and the common cathode is connected to our ground terminal. We also have a SG90 servo motor which has a signal pin connected to our digital pin 6, and the ground and VCC connected to our ground and 5 volts on our breadboard. So this is all the hardware, pretty simple stuff. This over here on the Jupyter is our code. I'm sorry, I was running some tests. So this entire code processes the image, loads the image, processes it, and then displays it on the on our kernels, and does all the work for it. I will go through a demonstration and you will see how it works. So I'm gonna start this now. There you go. I'll run that cell, and so now you can see all the information being shown on the serial terminal. And now you can see that one image has been already analyzed and the orientation has been correct. Same for the second one. There you go. So now it has fixed orientation. It is detecting an image again, fixed its orientation. Loaded a new image, detecting it again, fixed its orientation. Loading an image, detected it, fixed its orientation. Loading an image, detecting it, fixed its orientation. There you go. Done the part. Goes through these images pretty quickly. And then once we've gone through the entire thing, the shutdown is complete. So now how does our code portion work? So basically the images are first loaded. So I will go through the code and then I will tell you how it works. So basically we initiate our image folder, the port that we want to access. We also specify the certain pins and things that we have on our board for our Arduino connections. So the Python program basically what it does is it first reads all the images from that particular folder and uses glob and OS to collect the file names in a sorted order so that the program processes them in a sequence as they are named. Inside the main loop, each image is loaded with using cv.imread. This simulates a conveyor belt bringing in a new pen every 5 seconds. The image filtering. Once an image is loaded, it goes through several processing steps. First one is grayscale conversion. So the image is converted into grayscale. This simplifies the image because orientation detection does not need color information. Then it goes through Gaussian blur. Gaussian blur is applied to smooth the image and reduce fine texture in the background. This helps make the threshold more stable. Then blurred grayscale is converted into binary using Otsu thresholding. with binary inversion. This separates the pen from the background by turning the pen into a foreground object and the background into the opposite color. So as you would have seen right here, pen becomes black and the background becomes completely white, right? Then we have our morphological cleanup. So after the thresholding, the background still contains some noise and small specks. So the code uses morphological operations to clean the image, like opening to remove small isolated noise, dilation to strengthen and connect the pen region, and erosion to shrink the expanded object into a realistic shape. After this, the pen becomes much cleaner single object, which makes angle detection more reliable. Then we go into image analysis. After cleaning the binary image, the code finds contours and chooses the contour most likely to be the pen. It does this by ignoring smaller contours and fitting a minimum area rotated angle around each remaining contour, the calculating the aspect ratio of each contour, right? So then CV.min area rectangle is used again to select the pen, right? That's how it detects the pen. The normalized angle is the value used to decide how much the servo needs to rotate, right? OpenCV's raw angle can be inconsistent depending on the rectangle width and height. So the code normalizes it so that it consistently represents the long axis of the pen relative to the horizontal axis, right? So as you would have seen, like this rectangle, we've got a long axis and which is the horizontal axis. The RGB LED, basically, as soon as a new product is detected, the image is being processed and the angle is to be calculated, it remains red, right? The code goes through this very quickly, so it does not remain red for a long time, but it still remains red for a certain amount of time. After that, once the code calculates the pen angle and sends the correction angle to the servo, again, very fast things, so it changes the RGB LED to green. Green means that the servo has completed the correction command and the pen has been aligned horizontally. Then, of course, the Python code is printing for every program. It prints that line, the name of the image, its rotation angle, and the servo angle has fixed that, along with a side-by-side comparison of the image that it detected and the cleaned up just the pen against a black pen against a background image. So our rationale behind the erode and dilate parameters, the erosion and dilation settings were chosen to balance two goals. First one is to remove the background noise, and second one is to preserve the online overall shape. You can see it does that very easily, and you can also see that it detects this speck as part of the pen, so it still needs a little bit more fine tuning. But our main idea was to create an overall angle for the pen, which it definitely detects properly and actualizes that. So our program is a success. The threshold image still contains many small bright specks. So basically these caused by the textural background, right? So the code uses a 3x3 opening and repeats it multiple times for moderate cleanup, right? This is small enough to not erase the pen, but strong enough to remove these like smaller specks around here, as you can see, right? These small specks that you see, it will remove that. Then we use dilation, right? After opening, parts of the pen can still be thin or slightly broken. So dilation expands the white foreground region, so the pen becomes more connected and solid. So you can see that the pen becomes more connected and solid, yet we can still see that these regions which are more lighter do not get detected back in and do not become part of the pen. But yeah, so there are definitely still fine-tuned issues with the program, but our main objective is satisfied to a good extent, so we are fine with it. Why? So the dilation alone will make the object too thick, right? So we need to remove things to make sure that the object is small enough and consistent enough. So erosion is applied afterwards with the same kernel again and same number of repetitions. I think it is 3. This restores the pen to its original size and keeps it cleaner and more connected than before. So the practical reason behind these parameters is that the parameter for erosion is 3x3. It removes small noise but keeps the pen connected, and the 5x5 dilation strengthens and reconnects the pen body. Matching erosion restores the object, like 3x3 erosion again after dilation restores the object while keeping the background reduced, right? So it's more spread out, it's more consistent. And that is the program, that is the project. It works perfectly. I will attach the code along with the video. Thank you very much. Have a good day.